Let's jump right into this explainer. Most of the time, we kind of just think of the heart as this romanticized beating organ, right? But today, we're flipping the script. We are going to look at the cardiovascular system through a completely different lens, as an absolute masterclass in fluid dynamics and engineering. We're basically going to look at your body as a high-tech system of pumps, pipes, and a highly specialized fluid payload.
Get a load of this staggering number, 400 million. Over an average 75-year lifetime, your heart, specifically your two ventricles working together, will pump roughly 400 million liters of blood. To put that completely wild number into perspective, that's enough liquid to fill an entire lake that is a kilometer long, 40 meters wide, and 10 meters deep. It is just a phenomenal amount of work for a squishy little organ that weighs only about 300 grams.
So let's start with the ultimate distribution network and why we even evolved this massive pump in the first place.
Here's the deal. If you're a microscopic, single-celled organism, you really don't need a heart. You can easily get your nutrients and expel waste just by interacting directly with your environment through simple diffusion. But as organisms evolved, grew larger, and became more complex, that method completely failed. The distances from the outside world to the central cells buried deep inside the body became just way too vast. So evolution had to step in and design a high-pressure, dual-pump convection system. This allows fluid to rapidly circulate, ensuring a steep concentration gradient so that oxygen and nutrients are delivered instantly and waste is swept away before it builds up.
Okay, let's move on to the physics of flow and take a look at the engineering behind the pipes themselves.
Just like the electrical wiring in your house, your cardiovascular system follows strict mathematical rules. If you know a bit about electricity, you probably recognize Ohm's law. Well, it turns out there's an Ohm's law of hydrodynamics too. As the equation lays out, flow equals the driving pressure divided by the resistance. Basically, your left heart acts as a constant pressure generator. It creates the driving pressure, that massive push that forces blood against the friction, or the resistance, of your entire vascular network. It's an incredibly elegant balancing act. Way back in the 1840s, a physicist named Jean Poisson figured out the exact math for liquids moving through tubes. Poisson's equation tells us that flow is dictated by the driving pressure, the viscosity or thickness of the fluid, the length of the tube, and the radius of the tube. Now, sure, this law assumes the fluid behaves perfectly and the tube is completely rigid and straight, which, let's be honest, isn't entirely true for our squishy branching blood vessels. But it gives us a really critical foundation to understand how blood moves.
But honestly, the absolutely crucial takeaway here is that little r to the fourth in Poiseuille's equation. It is a literal game changer. It means that a microscopic change in a blood vessel's width dramatically alters the blood flow. If a vessel dilates just a tiny bit, flow skyrockets. But on the flip side, if an artery narrows slightly, say from atherosclerosis, the resistance shoots up exponentially. When that happens, your heart has to work vastly harder just to push the exact same amount of blood.
Now, as blood actually flows through all these pipes, it's not always smooth sailing. Normally, blood travels in what's called laminar flow. It moves in these silent, highly efficient, concentric layers, kind of like cars perfectly organized on a multi-lane highway. But if the vessel gets too wide, or the blood moves too fast, or an artery narrows abruptly, things get chaotic fast. This tipping point is determined by something called the Reynolds number. When that number exceeds 3,000, that highly efficient laminar flow suddenly breaks down into turbulent flow. The blood literally starts forming chaotic, swirling vortices. This turbulence is energetically wasteful, and more importantly, it's noisy. It creates acoustic murmurs, or bruits, that doctors actively listen for to detect blockages or heart valve issues.
So, measuring the machine. Now that we've mapped out the physics of the pipes, how exactly do we decode the signals and measure what's happening inside them?
Well, think about a tool you've definitely all experienced, the sphygmomanometer, better known as the blood pressure cuff. Believe it or not, it actually relies entirely on that turbulent flow we just talked about. When a doctor inflates the cuff, they completely block off the artery. Then, as they slowly release that pressure, blood forcefully squirts through the momentarily narrowed vessel, creating turbulent, noisy flow. Using a stethoscope, the doctor listens for those turbulent sounds, known as Korotkov sounds. The very first tapping sound they hear marks your maximum systolic pressure. Then, as the cuff deflates further, the vessel opens back up, smooth laminar flow returns, and the sounds muffle and disappear. And boom, that's your minimum diastolic pressure.
But we can get way more advanced than a simple pressure cuff. Take Doppler echocardiography, for example. Just like a police radar gun bounces sound waves off a speeding car to check its velocity, ultrasound probes bounce sound waves off your moving red blood cells. The machine then color codes the speed and direction of the blood.
The red colors indicate blood flowing directly toward the transducer, while the blue colors show blood flowing away from it. It's wild because it allows us to visualize the exact dynamics inside the beating heart in real time.
All right, let's shift gears and talk about blood, the liquid organ. We're transitioning from the pipes to the payload itself, because blood isn't just red water. It is actually a highly complex, living liquid organ.
If we break down the volume of blood, we can really see what makes up this liquid organ. If you take a sample of blood and spin it down in a centrifuge at super high speeds, it separates by density into the hemicrit. Down at the very bottom, making up about 45% of the volume, are the heavy, packed red blood cells that carry all our oxygen. Just above that is a tiny sliver, only about 1%, called the buffy coat. That holds your immune-defending white blood cells and your clotting platelets. And then sitting right on top is the remaining 54%. That's a pale, watery solution called plasma, which is absolutely packed with electrolytes and vital proteins.
And speaking of the proteins floating around in that plasma, comparing electrophoretic patterns actually solves a pretty common medical vocabulary mystery: the difference between plasma and serum. When we look at the pattern of proteins found in plasma, there's a massive band representing a clotting protein called fibrinogen. But if we allow the blood sample to clot first, that fibrinogen gets entirely used up to form the clot. The leftover fluid that we extract after that happens is called serum. So if you look at the serum's protein pattern, that fibrinogen band is completely stripped out. Essentially, serum is just plasma minus the clotting factors.
Which brings us to the magic of viscosity, and a pretty mind-bending non-Newtonian twist. For our final structural component, we have to look at the physics of how this liquid organ actually behaves in motion. Because frankly, blood breaks the normal rules of physics.
To really grasp this, we have to talk about viscosity. Viscosity dictates how easily a fluid flows. It's essentially a measure of the internal friction or slipperiness between layers of fluid as they slide past one another. Mathematically speaking, it's the force applied, the shear stress, divided by the velocity gradient produced, the shear rate. When Papoisio made his famous equation that we looked at earlier, he assumed that viscosity stays perfectly constant, no matter how much force you apply to the fluid.
Fluids that behave predictably like that are called Newtonian fluids. Water is Newtonian. Honey is Newtonian. If you tip a jar of honey, it flows constantly under the gentle pull of gravity. But here's the ultimate twist. Blood is highly non-Newtonian. It actually behaves much more like mayonnaise. Think about it. If you tip a jar of mayonnaise upside down, it doesn't move. It's completely immobile until you apply a specific threshold of force, like scooping it with a knife. That critical threshold is called a yield shear stress.
So why on earth does blood act like mayonnaise instead of water? Well, it all comes down to chemistry. The interaction between those large fibrinogen proteins we saw earlier and your red blood cells cause them to essentially stick together at low speeds. This creates that yield shear stress. It means your heart literally has to apply a massive initial punch, a strong driving pressure, just to break that internal friction and get this non-Newtonian fluid moving in the first place. Once the blood gets up to speed, the cells perfectly align, the friction drops, and it flows beautifully. But without that initial forceful heartbeat, your blood would quite literally stand still in your veins.
It is just this incredibly delicate, brilliantly engineered balance between fluid dynamics, biological proteins, and pure physical force. As you consider the mind-blowing hydrodynamics keeping you alive right this very second, from the exact millimeter radius of your arteries to the bizarre, non-Newtonian flow of your plasma, it really leaves you wondering, what other miraculous, self-healing, incredibly adaptable physics are quietly operating inside your own body right now without a single conscious thought from you? Thank you so much for exploring the mechanics of the human machine with me in this explainer today. Keep asking questions and keep learning.